generator as such. So today we will be starting with synchronous motors. Okay, so let us not waste any more time and let us start with the basic definition of a synchronous motor. Now you know that a motor is a device. Okay, what is a motor? A motor is a device which converts electrical energy into mechanical energy, right? Converts electrical energy into mechanical energy. So a synchronous motor is a synchronous machine. Okay, it is a synchronous machine. It is a synchronous machine that converts the electrical energy into mechanical energy. Another important point about the synchronous machine is that the synchronous machine is a doubly excited machine. Okay, so we will come to what is doubly excited, etc. Anyway, for now you understand that the synchronous motor is a doubly excited synchronous machine. Now, for that, now let us, in today's session, we'll be going through the basic working of the synchronous motor. So for that, let us draw the synchronous motor or the synchronous machine, the alternator which we have discussed so long. Let us draw the same machine, because generator or motor, the construction of the synchronous machine is almost exactly the same. So the constructional feature you can use like what you have used in synchronous generator. So now, because the synchronous machine, alright, for whether it be a motor or the generator, the construction is almost the same. We can use the same concepts what we have used for the alternator, okay, or the synchronous generator. So this is the outer structure of the armature. Okay, so now let us draw our coils. Okay, so you know that this coil, let us call it as A, and the coil will have other side A dash. Okay, and what was the winding properties? It was a three-phase electrically separated windings. Okay, now because this is a two-pole machine which I am going to draw, with respect to the armature, it's a two-pole machine. So the mechanical angle and the electrical angle will be exactly the same. So the second coil will be here. So this is B and this will be B dash. So this is 120 degree separated. So this is here. So this angle is 120 degree. And the third coil will start here, C and C dash. So this is the armature. Okay. So other than the armature, you had a field, right? So this is the field. So this is a salient pole type of field that we are going to use. Okay. So in case of an alternator, what you did was that you gave mechanical energy, or you gave a prime mover torque to this rotor. Okay. In this case, field is the rotor. And when this was rotating in the air gap, you were getting a three-phase waveform out of all the coils together. Okay. So that was the alternator working principle. So now in synchronous motor, the concept is different, because here we are going to supply electrical energy. Okay, so where do you supply electrical energy? You supply electrical energy to the coils. Okay, so for example, to this A coil, you supply A phase, and to the B coil, you supply the B phase, and for the C coil, you supply the C phase. And what will be the characteristic of this electrical supply? It will be a three-phase voltage. Okay, it will be a three-phase voltage. Now, when you apply three-phase voltage in windings which are separated by 120 degree electrical, okay, 120 degree electrically, if you supply three-phase supply to three-phase windings, what do you get? You get a rotating magnetic field, right? So you get a rotating magnetic field. So now let this be the direction of the rotating magnetic field. Okay, so let me just draw a vector here. So this is the stator magnetic field. In this case, armature is the stator. So this is the rotating magnetic field which is produced by the stator. So to show that it is rotating, I will show it by this direction. So let it rotate in the counterclockwise direction. And what speed it will be rotating? It will be rotating with the speed of the synchronous speed, right? It will be rotating with the speed of the synchronous speed. Now, to the field, what do? You connect a DC source to the field, right? So when you connect a DC source to the field, you will get a DC magnetic field. Okay, you will get a DC magnetic field. So let me call that as the BR. Okay, so let me call it as BR. Okay, so now you are having two fields here. Okay, now you know that when you are having two fields, there will be a torque induced. In case there will be a torque induced in this rotor, which will be a function of K into BR cross BS. Right, this equation we have seen a lot. We use K into BR cross B net as well, but in this case we are having two fields of BR and BS, so we are going to take BR and BS here. So the torque induced will be K into BR cross BS. That means the direction of the torque induced will be proportional to the direction of BR cross BS. Right, it will be proportional to BR cross BS. Now look at this here. This BS is at this point here. So what will be the direction of the torque induced? The torque induced will be in this direction, right? So BR crossed with BS, BR crossed with BS is a counterclockwise direction. So this will be the direction of torque induced. But this BS is not stationary, right? See, basic property is that when you are having two magnetic fields, they try to align with each other. So, but BS is not stationary here. BS is rotating with the torque, with the speed of omega c. Now, for that, this BR also will try to catch up with BS. However, it will not be able to catch up with BS, but it will try to catch up with BS, and this also will rotate with the speed of omega c. So, BR is going to shift its position. So, by shifting its position means that the rotor will have to come to a new position. So, if the rotor is in this direction now, the rotor is like this now, okay. So, this will be the new value of BR, and by that time the BS might be somewhere around here, okay. So, that is the basic thing here. So, I will just write down some points here to understand this. So, this is how the rotor starts rotating in the synchronous machine. So, just write a few points here. The field current IF produces a steady state magnetic field BR. Okay, that is what I have explained, steady state magnetic field BR. Okay, and when you supply three-phase currents, when three-phase subcurrents are given to the armature, which has three-phase windings, okay, it produces a rotating magnetic field. It produces a rotating magnetic field. In this case, the rotating magnetic field, I assumed it to be counterclockwise direction. Okay, and what happens? The rotor tends to align with the stator magnetic field, right? The rotor tends to align with the stator magnetic field. Okay, and the torque induced direction will be proportional to BR cross BS, right? So the direction of torque induced is the direction of BR cross BS. Okay, and so since the stator magnetic field is rotating, in the process of trying to align with the stator field, the rotor also rotates. So it is kind of getting magnetically locked with each other. So they are both getting magnetically locked with each other. Okay. Now, there is an angle between this BR and BS, right? There is an angle between this BR and BS, and we usually call that angle as delta. See, this is BR and this value is BS. So there is an angle between these two, and this angle was delta. So more the angle delta, more will be the induced torque. That also we have seen in alternators also. So here also that same thing is going to be valid. So the larger the angle between the fields, the more is the induced torque. Okay. So you can conclude by telling that the rotor chases the stator magnetic field. The rotor chases the stator rotating magnetic field in a circle, never quite able to catch it. The significance of all this angle delta etc. will come in the future sessions. Now, one important thing that you have to remember here is that I have told about the steady state operation of the synchronous generator. Okay, so the rotor is already rotating, and I have just explained you how the rotor is rotating. That's it. Okay, I have just given you the steady state explanation of the synchronous motor. Sorry, I have not told you how it actually starts rotating. Okay, that is a concept which is for another topic, because the synchronous motor is not a self-starting motor. So if you just switch on if the rotor is stationary and if you just switch on the supply, the rotor is not going to rotate. It is not a self-starting motor. Alright. Whereas an induction motor is a self-starting motor, but synchronous machine is not a self-starting motor. So that will come in another session, in a future session. I don't want to confuse with all the topics at once. So for the time being, you can just understand that the torque induced is in proportional to the direction of BR cross BS, and the rotor chases the stator field in a circular direction because the BS is also rotating in a circular direction. Okay, so I hope you have liked today's session. So this is a very simple beginning, and we will go to more advanced concepts.